All right, continue on. Before I erase this, I want you to look at the slide and look at the far left, resting potential. The condition of rest, negative 70 millivolts. It's established primarily by the leak channels. In particular, the potassium leak channels. Negative 70 is close to negative 90, the equilibrium potential for potassium. So associate the condition of rest with what we talked about here, the leak channels and with the pump counteracting the leak to maintain that negative 70. So if you stimulate the cell, what happens? That's what I'm going to talk about next. Well, you have all these other kind of potentials besides resting potential, graded threshold action potentials. They all mean different things, but they're all basically trying to get you to the action potential. This is the form of signal that we want to talk about. So to kind of explain the different potentials, you have to understand the different kinds of channels that carry the charge. So for the negative 70 for rest, that's the leak channels. When you stimulate a cell, first consider graded potentials. Graded potentials, when you try to stimulate a cell, use the ligand-gated channels. There's a picture of a ligand-gated channel on the left. That is where, let me write the term down, ligand-gated channels. This should be reviewed. We talked about the ligand-gated channels before at the motor end plate. When, in that case, the ligand was ACH, and what did it bind? ACHR. That allowed for sodium influx. Same thing. That sodium influx, it depolarized the cell. Now, graded means it could be a big stimulus or a smaller stimulus. Or it doesn't even have to be a stimulus. It could be an inhibition, okay? So the graded potentials can be a big or a small stimulus, or they can even be inhibitory. But they depend on the ligand-gated channels, okay? Graded means big or small. There's not like one size. It's like, it's graded. Like, you could get a grade in this class. Is there a difference between A or an F? To you, yeah. There's a gradation. That's all it means. Big or small in this case. So for the graded potentials, think about the ligand-gated channels. And we'll take a look at that again. For the voltage-gated channels, that is for the action potential. I described how those work before. A change in voltage will open the gate, not a ligand binding. Now, if you look at the slide here of the voltage gated channels, pay close attention to the membrane potential. Notice that it's negative on the inside here. When it changes to positive on the inside, that opens the gate. Okay, that's what I had described before. And the sodium is allowed to inflow. I want to go back to the previous slide. Let's look at the part of the cell where you find them. You see this where I put the number 4, action potential? What part of the cell is this called? Axon. That's where you find them. That's where you find the action potential propagating at a certain velocity down the axon so it can stimulate the next cell. Okay. So I'll put axon, that's where they're located. So for graded potentials, you're trying to stimulate a cell to fire. It's in a state of rest. If it's to respond to a stimulus, there are 3 places you can synapse onto it to stimulate it. And this figure kind of shows that. Let's review it. I actually mentioned this before, but it's been a while. What this figure is showing you is 3 presynaptic cells synapsing onto a postsynaptic cell. 3 neurons, call them presynaptic cells. Synapsing, making a connection with, synapsing onto a postsynaptic cell. At 3 locations. One area of input is the cell body itself, the soma. Another area of input could be the dendrites or the axon hillock. This is my postsynaptic cell, and one area you could synapse onto it are those little branches called the dendrites. The dendrites, they have all of these neurotransmitter receptors, whether it be ACH, epinephrine, dopamine, whatever neurotransmitter you're talking about. And you can synapse onto it. You can synapse onto. I'm just drawing the axon of a presynaptic cell. That's pre. That's the synapse, that's the postsynaptic cell. You can synapse onto the cell body. So you zap it right on the cell body, or you could synapse right onto the axon hillock. Okay, that's kind of what the picture is showing you, right? The presynaptic cells are synapsing onto the postsynaptic cell. At 3 locations. So to give you a close-up picture of what's happening there, here's this picture here. We've kind of studied this before. Neurons generate and conduct electrical signals called action potentials. So assume the three presynaptic cells have generated action potentials. You write that down. Neurons generate electrical signals called action potentials before the break. If they're resting, they're negative 70. But if they generate these action potentials, they conduct those electrical signals. You must transmit a signal across a gap called the synapse between the cells. You must transmit a signal across a gap, which we're calling the synapse. And I don't think this isn't anything new, right? We kind of talked about this picture before. Because when the action potential arrives, when the electrical signal arrives, it stimulates the quantal release of ACH. I'll just say when AP, action potential, arrives, it stimulates the quantal release of the neurotransmitter, say for example ACH, into the synapse. So that kind of explains what you're seeing here. This was actually on the previous test, except the postsynaptic cell wasn't another neuron, it was a muscle fiber. So it's the same conversation. So it's nothing new, in my opinion. This presynaptic neuron, an action potential is being generated. It arrives, there's calcium influx. That causes the fusion of these ACH vesicles. They fuse, and in quantal bursts, they release the ACH across the synapse. So that's the signal. The signal between two cells is not electricity. It's a chemical. It's ACH. But what that does is it opens the ligand-gated channels and allows sodium influx in an attempt to stimulate the postsynaptic cell. So at each little synapse here, imagine there's ACH and there's sodium influx. Okay? So each of these, there's like a sodium influx, and a sodium influx. And what you're trying to do is, these are graded potentials with ligand-gated channels. So I'll put graded potentials. They're ligand-gated channels. Ligand-gated. Is it enough of a jolt to get enough positive charge? It's like you're trying to build the positive charge in all these locations. You're trying to get it to like kind of focus to here, to the axon hillock, where you are gonna have the voltage-gated channels. If you get enough positive jolts to like get this cell to have the positive charge to move here, the first segment of the axon, if you can stimulate those voltage-gated channels to open on this first segment, you'll get an action potential. Okay, so that's what you're doing. You're trying to stimulate that cell. This is showing you a close-up of, look at that picture, the quiz question was, what kind of channel was that? Leak? graded, leak, ligand, or voltage gated. That one is ligand gated. So what it's showing you is the green ball is the ligand. You get your ion movement, and your graded potential, the ions can flow across the surface on the inside and the outside of the cell membrane. That's what it's showing you there. Then, of course, you have enzymatic degradation. We talked about that before. I mentioned ACHE, right? Well, anyways, when you kind of give a postsynaptic cell a jolt, you can kind of measure it in the lab. You can see these little teeny weeny depolarizations, right? Okay, so let me erase this. So to list some properties of graded potentials, which is what you're seeing here. I'll review what I've already stated. What kind of channels do they depend on? The ligand-gated channels? Yeah, you got that down. Okay, basically, well, they're not really big spikes. They're very small. I use the term teeny weeny depolarizations. They could be bigger. They're graded. I mean, they're called graded potentials. That means they could be bigger, they could be smaller. You can add them up. Maybe two small ones equals one big one, and that might be enough to get the cell to fire. They're graded, they can be big or small. They're graded, but they can summate. I'll talk about that towards the end, but yeah, you can add them up, because like with what I just erased, you synapsed at 3 places. So what if all 3 of those places you fired at the same time? You got 3 jolts. They could add up and stimulate the cell. The goal of understanding these, you're trying to reach some threshold potential that will turn on those voltage-gated channels. That's kind of the goal here. You're trying to reach some threshold potential that will trigger a full-blown action potential in the axon. Because remember, the axon, is that the area of input or output? The axon. That's the area of output. You're trying to get that going so that cell is stimulated and will stimulate the next cell. That will trigger an action potential in the axon, the area of input. Okay, that's the goal here by studying all these little teeny little blips and dips. There's some threshold. If it's a big enough jolt, the cell will fire. Okay. Remember when I taught the size principle? It was even a test question. I said, cell size, one was bigger, one was smaller. Which cell was easier to stimulate, the big cell or the small cell? The small cell was easier. That's what's going on here. It's easier to stimulate a smaller cell. So you don't have to give it as big of a jolt to get it to fire. So, like for example, what you're looking at there, you can actually measure it in the lab. So here's our negative 70 millivolts. Okay, we're at rest. And you give it a little jolt, say stimulus right there, and it kind of depolarizes and then kind of. So not only are they small, They die fast. They're decremental. That's another property you should list to this list here. They die fast. So at the point of stimulation, it goes back to rest. So you're at -70, or rest. At the point of stimulus, you open those ligand-gated channels and you measure a depolarization. Usually it's sodium influx. Okay, so maybe you go from -70 to -65. You're a little less negative, a little more positive because of the sodium influx. But then when you go back to -70, maybe there was some potassium efflux. So we continue here. And that returns you back from -65 back to -70. So they die fast. You go back to rest. What I mean is, it doesn't persist at -65 for an extended period of time. They poop out really fast. They just go away. Okay. Again, the goal is you're trying to give a big enough jolt so you can get those voltage-gated channels to fire in the axon hillock. Maybe -65 wasn't enough of a jolt. Maybe the threshold potential for this given cell is, maybe it's -55. Maybe that's the threshold potential that would give you an action potential. Just let's pretend it's negative. So let's give it another jolt. Oh, not quite. Okay, you're trying to reach threshold. And if it's not a big enough jolt, if you don't quite reach threshold, you just get no stimulus. So these graded potentials, I guess, were for nothing. Okay. But what we'll see is if you can give it a big enough jolt, if you can reach threshold, you'll get a big spike. And that's the action potential, but that's Wednesday's lecture. But the goal is off or on, right? Off. You gave it a stimulus, a graded potential, but you didn't get your big spike or action potential. But if you can reach threshold, on, you get the big spike. But that's for later Wednesday. Okay, well, if you're trying to stimulate a cell, the goal is to reach threshold. Sometimes you don't want to do that. Sometimes you want to inhibit a cell on purpose. If you want to inhibit a cell, this is a good way to inhibit it. Bring it further away from threshold. They call that a little hyperpolarization. But it's still a graded potential. It's just inhibitory. So here's our -70. All units are millivolts. Here's our threshold potential, -55. We're going along at rest. And you stimulate here, and you open cells in a way where you actually go like that. Okay. Any stimulus that takes you further away from threshold is, well, it's a hyperpolarization. That's what we call it. When the cell is polarized in the condition of rest, it's -70. It's way more negative on the inside than the outside. If you make the inside of a cell even more negative, it's like hyperpolarized, right? So at the point of stimulus, you're at -70. Then you stimulate. And then say you have some hyperpolarization. hyperpole. Maybe it's due to potassium efflux. Some positive left the cell, made the inside even more negative, maybe negative 75 millivolts. Okay, it's kind of the reverse of here. And then maybe that follows with some sodium influx to bring you back to negative 70. So literally that's what's happening there. And any stimulus that takes you further away from threshold is inhibition. So right here, inhibition. Because threshold's like way up here, you go farther away from it. That's a graded potential to inhibit a cell. They have some, I included some figures to kind of show you better pictures of what's going on in the cell membrane. Any questions on depolarization versus hyperpolarization?
Why would you want to inhibit?
Let's say you want to flex. So I want to stimulate this muscle, but I want to inhibit my triceps. So you have neurons that inhibit the motor neuron for the opposing muscle, antagonist muscle. So they're trying to illustrate Ligand-gated channels, and they show you all the things that we were talking about this morning. You can measure the membrane potential at negative 70 in a condition of resting state. If it responds, the ligand-gated channel binds, and they light that membrane red. Because what's going to happen is these positive cells now enter the cell. You're depolarizing the cell by allowing the positive in. It goes to negative 65. Okay? And then they show this local current. This current that you've let in will now look around on the inside and see it's all negative, and that current will flow along the surface on the inside. Okay? So that at the point of stimulus is negative 60. But as that positive charge flows outwardly, it depolarizes neighboring parts of the cell. So this is negative 65. Then it dies really fast, that's negative 70. So that's what they're trying to show you here. Okay? This negative 60 isn't instantaneously spread on the whole cell. This local current has to travel, but it doesn't travel very far at all. So it's like, if you go from, well, let's look at it this way. Let's say this big sheet represents the cell membrane of the cell you're trying to stimulate, this whole big thing. And let's say you zap it with the ligand-gated channels right here. You make them open. See right here. Positive charge goes at this point. Like throwing a stone in still water. The ripple effects go out, but the ripples die out. Okay? So let's say zap right there, and it kind of like goes out. Maybe it dies right there. Okay, but right where you throw the stone in, right where you zap it, maybe it's like negative 60. But as you get to the outermost ripple, maybe it's like negative 69, and it's negative 70 everywhere else, right? It only gets depolarized at the point where you stimulate. But let's say you give it a harder zap. Zap it right there, zap, and it's a bigger zap, and those ripples go out much further. Okay, maybe where you zapped it, maybe it's negative 55. Maybe that's enough to reach threshold. Okay, so these graded potentials, it can be, smaller or bigger, but they die fast. The bigger zap you give it, the more the ripples can travel and perhaps stimulate the whole cell. So I think that's what this figure is trying to show you. There is some local current. Once you let the sodium influx in, they kind of flow all around. So they show it again here. The stimulus is you just kind of physically poke the cell, and that kind of stimulates it. And that once you let the positive charge in, it flows in any direction it can. Okay. Here's a good picture. You know, I always put this figure on the test, and most students miss it. Okay. So even though I tell you it's on the test, you have trouble with this one. Why don't you like put a star next to it? It's a figure showing you the decay of membrane potential with distance. Because current is lost through the leaky plasma membrane, the voltage declines with distance from the stimulus. The voltage is decremental. That's the key word. What does decremental describe? What kind of potential? Graded potentials. There's resting potential, there's graded potential, there's action potential, there's threshold potential. I use the key word decremental to describe the graded ones. You stimulate right there, you depolarize the most, but as you move away, it kind of like dies really fast. That's what I'm trying to show you there. So this figure represents this decay of graded potentials. Kind of like this. As you get farther away, the depolarization, you're losing it. Okay. Oh, okay, I was into that. For lab today, I asked you to print out the neuron lab. It's essentially a worksheet. I wanted to give you class time to work on it today, but it's not due till Wednesday. So if you don't need to work on it today, you're free to go. But I encourage you to stay here if you want to work on it, so I can help you. All right. Be sure to turn in your half sheet. Leave a pile over there, kind of by the torsos. Get that turned in for your points for the day. We'll teach action potential on Wednesday.